my name is Sangmi Kang, and I will present my research on risk factors and safety strategies for railway level crossing accident, evidence from Korea. I will briefly cover the introduction, data, and methodology, and key results including policy simulations and conclusions here. Railway level crossings are really unique infrastructure where trains, pedestrians, and vehicles intersect at the same point. So if there is an accident and the result is really severe, because the trains are extremely massive and it's hard to stop because of the long braking distance. So even though the train driver sees an obstacle on the track, it's really impossible to avoid a crash. Please look at the first graph on the left. It shows the annual number of level crossing accidents from 2018 to 2024. The general trend is declining, but accidents still occur every year. And on the right, out of 487 total accidents during this period, 60 cases happened at level crossings, with a fatality of over 36%. Accidents at level crossings are rare, but they are extremely dangerous. That's why we need to understand which factors make them fatal and how we can reduce the risk. Previous studies on level crossing safety have moved from frequency-based analysis toward severity-oriented modeling, but I found three major gaps here. First, many studies identify risk factors, but they don't quantify how much a certain action or policy would reduce the probability of a fatal outcome. And second, the data sets are too small, so common approaches like data pooling or binary collapse are applied to handle this problem, but they lose critical severity detail. And third, findings vary across countries, and severity analysis grounded in Korean data remains limited. So to address these gaps, this study applies SMOTE-NC to handle the data challenge and multinomial large model to analyze severity, providing quantitative evidence for safety policy decisions. I collected the data from two sources, KORAIL Internal Accident Report and Rail Safety Information System covering 7 years from 2018 to 2024. The primary data gave me detailed information like the train speed at the time of the accident, crossing type, and people involved. And I used the RLCs data to confirm that I had captured all the cases. The initial data set was 60 cases, and I excluded 7 suicide cases because they reflect intentional behavior rather than accident risk factors, leaving 53 cases for the final analysis. Now let me explain how I define and classify the variables. On the left side, there is an accident severity classification. The dependent variable is accident severity. At first, I classified it into 4 levels like PDO, meaning only property damage, and minor, and serious, and fatal injury. However, there was only 1 minor injury cases, so I merged it into serious injury group. And the independent variables were divided into 4 groups: temporal, environmental, operational, and human-related factors. So you can have a look at all the variables I used here. And all variables were dummy-coded, so I got 21 binary features in total. And missing train speed values were filled in using the median speed for each train type. And all cases were manually verified using KORAIL Internal Accident Report one more time. Now this is what the original data actually looks like. On the left, there is a donut chart showing the original severity distribution. About half was PDO and the other 50.9% accounted for fatal or serious injuries. And looking at the key patterns on the right, the most important finding is that vulnerable road users had the fatality rate of about 64%, by far the highest among all groups. And gate violations had a fatality rate of 40%, and elderly users were about 33%. And also nighttime and mid-speed and unmanned crossings showed higher fatality rates. However, descriptive statistics only show us the raw patterns, so I developed a formal model to provide a more robust analysis. To analyze the small data set, I considered three options. The first one was to use the original data directly, but this leads to unstable result with unstable coefficient. The second option was to combine three severity levels into two, like fatal or non-fatal. But that loses the important distinction between serious and fatal injuries, which read critical to my study. So I chose the third one, SMOTE-NC. This is a machine learning technique to create synthetic new cases based on the pattern of the original data. It is designed to work with both continuous and categorical variables, and I will explain how I validate this method in the next slide. To validate SMOTE-NC, I split the original data into 5 cases for the test set and 48 cases for the training set. Then I augmented the 40 training cases using SMOTE-NC, expanding them to 240 observations and estimated a multinomial large model on this dataset. The result shows 80% accuracy. The test set included only one fatal case, and the model correctly predicted it, achieving an F1 score 1. This confirms that the augmented data preserved the patterns needed for analysis. And after this validation, I augmented the full 53 cases and used all 265 observations for the final model. For this study, I used a multinomial large model. I didn't use ordered logic because it assumed the same risk factors affect all severity levels in the same direction. But I expected that a fatal accident might have completely different drivers than serious injuries. And the MNL model allows each severity level to have its own set of effects. And I used PDO as a reference. All coefficients I estimated show how each variable changes the probability of serious or fatal injury compared to PDO. The model fit is strong. The likelihood ratio test is highly significant with a chi-square of 130.85, and the pseudo R-squared is 0.239. This confirms that the model fits the data very well. Once the model was estimated, I ran counterfactual simulations. The idea is very simple. If I change one condition in a real accident, for example, if a nighttime accident happened during the daytime instead, how much would the fatal probability reduce? The process is straightforward. I apply the estimated coefficient from the augmented data set to the original 53 accident. Then I changed one condition at a time and observed how the fatal probability changed. The baseline fatal probability was 16.1%. And it is really important to remember that this is the conditional probability of fatal outcomes, given that an accident has already occurred, not the probability of an accident happening in the first place. These are the estimation results from the MNL model. A positive coefficient means higher risk, and a negative one means lower risk compared to PDO. I will explain each finding in detail later, but there are some key patterns here. Vulnerable road users show the largest coefficient in the entire model, 4.56 for the fatal injury. And unmanned crossings show a coefficient of 2.006 for fatal injury. These are the two strongest drivers of the fatal outcomes. And low train speed and daytime condition reduce the risk of fatal outcomes. And the rest of the variables are all related to the serious injury. These are the key findings. The first group covers human-related factors. First, as I mentioned before, vulnerable road users have the largest coefficient in the entire model. So when an accident occurs, we have no structural protection at all. So they take the full impact of the train directly. The second, elderly involvement showed an unexpected result. The factor was actually related to the lower serious injury. So one possible explanation is risk compensation behavior. Elderly people may already be aware of their physical limitations, so they tend to cross more cautiously than we think. But this needs further validation. And third, stalled vehicles mean cases where a car gets stuck on a crossings and cannot move. These cases are linked to higher serious injuries, but not fatal ones. A possible reason is that the car driver may evacuate before the crash. The second group is infrastructural and operational factors. First, unmanned crossings show a fatal injury coefficient of 2.006, the second strongest in this model. At unmanned crossings, there is no real-time monitoring and nobody to warn people when a train is coming. So road users must rely on their own perception. When they fail to detect a train, the result is often fatal. Second, low train speed reduces both serious and fatal injury risk because lower train means less impact energy and more time to react. Third, passenger trains are associated with lower serious injury compared to freight trains because they have lower mass and cause less impact force. Finally, local partition crossings show lower serious injury rate than national crossings. This is likely because they have lower traffic volumes and road conditions are quite simple. And the last group covers temporal conditions. Daytime accidents are much less fatal than nighttime accidents. And as we all know, at night, visibility is worse and warning signs are hard to read and drivers may be more tired. So all of these factors combine to make the nighttime accident more severe. For weekend conditions, we show the marginally significant association with higher serious injury. One possible reason is that drivers are less familiar with local laws and crossings on weekends. But this result is only marginally significant, so I will not overinterpret it. Now I will present the counterfactual result here. As I said, the baseline fatal probability was 16.1%. Using the significant variables from the MNO model, I created 4 policy scenarios. Scenario 1 looks at what happens when pedestrians and cyclists are not involved in the accident. So here I set the vulnerable road user variable to 0. So the fatal probability drops to 14.07%, which is a 12.6% relative reduction. And it is helpful, but the smallest effect among the 4. And scenario 2 enforces low train speed. The fatal probability drops by 32.2% and is a meaningful improvement. And scenario 3 shows the strongest effect. Here I set all unmanned crossings to manned, meaning they are upgraded to active control systems. This dropped the fatal probability from 16.1% to just 3.84%, a 76% reduction, by far the biggest effect. Scenario 4 improves the visibility by setting all cases to daytime conditions, 17.4% reduction. So as shown at the bottom, the scenarios are ranked from the largest to the smallest effect, and each one comes with a key strategy. So I will present these as a safety policy roadmap next. Finally, I would like to propose a safety policy roadmap based on the simulation result. In the short term, I recommend enforcing speed restrictions at high-risk crossings. This is a feasible option that can be implemented quickly at a low cost. In the medium term, installing LED lighting and retroreflective warning signs and nighttime crossings would be effective. For the long term, upgrading unmanned crossings to intelligent active control systems is the most critical step. This means AI-based obstacle detection connected directly to incoming trains. At the same time, grade separation and physical barriers should be installed to keep pedestrians and cyclists away from the crossing area. To wrap up, this study contributed in 3 ways. I applied SMOTE-NC to overcome the small data issue, confirmed that vulnerable road users and unmanned crossings are the primary drivers of the fatal outcomes, and translated the findings into a phased safety roadmap. And limitations include the small data size and the ceteris paribus assumption and simulations. In the future, I will focus on expanding dataset and adding confidence intervals for more robust estimates. Thank you for your attention, and I look for your questions and comments.